Precision Measurement for Machinists, a Master Task Multimedia Program. Lesson 1. Basic Print Reading. In the machining industry, most parts are manufactured for the purpose of mating or functioning with other parts. Therefore, all of the components must match up and mate together satisfactorily for the device to achieve its purpose. To ensure that components or parts work together properly as part of a whole, a standard must be given for parts to be measured against. These standards are known as the inch and metric measurement systems. Gaining proficiency in using both systems will greatly enhance your ability as a machinist. But in order for you to machine parts to their specifications, you must be able to locate and correctly understand the information that describes what a quality finished part looks like. You will find this information or data on a part print. Think of the print as a road map that leads you from where you are now, with a raw, unfinished workpiece, to your destination, a finished part. In order for you to get to your destination, you must be able to understand the map. In this lesson, you will learn to read and interpret the values and symbols found on a part print and follow the path to producing an acceptable part. There will be 4 parts to this lesson. In Part 1, you will learn about part prints and understanding dimension information. Part 2 introduces and explains symbols that appear on a print. Part 3 explains the title block and tolerances. And Part 4 introduces the 2 common systems of measurement. Part 1. Viewing the print and understanding dimension information. All workpieces are 3-dimensional objects which have a length, width, and depth. Since part drawings are 2-dimensional, different views must be utilized to illustrate all of the features accurately on a print. Most prints are either 1-view drawings, 2-view drawings, or 3-view drawings. It is possible that a drawing may have up to 6 normal views, along with other specialized views as needed. A view is a drawing which depicts the way the object will look when viewed from a particular direction. For example, here is an object with its front view and side view. These 2 views would be adequate to identify all the features of this relatively simple object accurately. Each view has dimensions noted that describe that view. A dimension indicates the size of a feature. Here is a print for a cylindrical object. It only requires a front view and a side view. There is no need for a top view since it would be the same as the front view. Only more complex objects will require 3 or more views on a print. Each view is placed in a specific location on the print. The top view is always placed above the front view. The side view is always located on either side of the front view. A right side view is more common, but you may have a right side or a left side view. Think of the views as if the print were folded around the object. Each view represents the way the object will look when viewed from that position. On some prints, a 3-dimensional representation of the finished part may be provided. This is called an isometric view. You may also see one of these views drawn in section. A section view will show part of the material cut away to reveal internal features. When material has been removed for this purpose in a drawing, section lines are used to identify the cutaway area. Section lines are usually diagonal lines drawn in the cutaway area. Section lines can also be drawn using several other patterns. This means that the workpiece is made from a specific material. For example, this cross-hatch pattern indicates that the workpiece is made of either aluminum or magnesium. The upper half of this drawing is shown in half section. It appears as if the workpiece has been cut through to the center from the top and side of the part. 1/4 of the part is shown cut away. A full section would have shown the part as cut completely through from top to bottom. 1/2 of the part would be shown cut away. Other views may be provided on a print as well. The area within this circle is labeled B. The features within this circle are too small to be noted from this view, so another larger scaled view of the circle area is provided. This is called a detail view. The capital letter B refers to a detail view letter B located at the bottom of the print as you see here. The larger scale of the feature allows you to see important information about that feature. When the actual dimension of an object cannot be shown with any of the conventional views, auxiliary views may also be provided. For example, the diameter of this hole drilled at an angle cannot be shown. All normal views will display a foreshortened view of the hole, which would not be accurate. Because the hole is at an angle, the front and top views cannot show the true shape or features of the hole correctly. You can see from this side view that the center line of the hole is at 45 degrees, so this auxiliary view is drawn at a 45-degree angle from the side view in order to see the true shape and features of this hole. Dimensions and part features are located on the print using lines. The center of the workpiece is one feature commonly identified. The center line is the thin dashed line which passes through the exact center of the object. On older prints, you may see the letters CL representing center line. This line has a specific long dash, short dash pattern, so it can be easily distinguished from the other lines on the print. The lines which represent the edges of the workpiece are generally drawn thicker than many of the other lines on the print. These are known as object or visible edge lines. These lines represent the edges of a feature which can be seen when actually looking at the object from that view and are drawn as solid lines. Hidden lines, those edges of features which cannot be seen from a particular view, are drawn with a thin, consistent dashed pattern. Dimensions are found with the use of two types of lines, extension lines and dimension lines. These are extension lines. The purpose of extension lines is to extend a feature out from a view so that characteristics of that feature can be easily described without interfering with other features on the print. These are dimension lines. These lines point with arrowed ends to the set limits of a dimension established with the extension lines. When the space between extension lines is too small to write in the data, dimension lines may also be found outside or alongside the extension lines. A leader line may also be used to point from the dimension information to an extension line or directly to a feature. Extension, dimension, and leader lines are all drawn as solid thin lines so that they are easily distinguished from object lines. When a section view is required, a cutting plane line like this may be found. The cutting plane line, also called a viewing plane line, is typically drawn as a thick line with a pattern consisting of one long dash followed by two short dashes. A cutting plane line can also consist of thick dashes of equal length. The letters with the cutting plane line identify the section view to be found on the print. In order to understand how a cutting plane line works with the section view it refers to, you must first understand the basic principles of a plane. A plane is a flat surface. At least 3 points are needed to define a plane. In this example, you can see that a point identifies one single location. A line can be defined by specifying 2 points. A plane can be defined by specifying 3 points. The dashed line identifies the location of the plane along which the workpiece would be cut to obtain section view A. The arrows on the cutting plane line indicate the direction of view in which the section drawing is shown. On this print, section view A is defined by cutting plane line A. If the part were cut all the way through along cutting plane line A, and the piece that the arrows point to turned in order to see the cutaway area, we will see the features represented by section view A on the print. Cutting plane line B on this print, however, is much more complex because it does not cut straight through the part. It follows a route that will make these two holes visible in section view B. If the part was cut through along cutting plane line B and the piece that the arrows point to is turned in order to see the cutaway area, we will see the features represented by section view B on the print. If you encounter a print with a section view but no cutting plane line, look closely at the print. If it is obvious how a section view relates to a normal view, the cutting plane line is omitted to conserve space on the print. Note the section lines shown here. You can see that this is not a section view. Instead, it is drawn as if part of the workpiece has been broken away to reveal features that lay underneath. The thick line shown here is a short break line. It is the boundary that shows which part of the workpiece is drawn broken away. These are long break lines. They are thin lines, and their shape indicates that there is more to this feature than is shown in the drawing. The additional part of the feature is not drawn to conserve space on the print. The dimension of a feature using a long break line is always underlined. This means that the feature is not drawn to scale with the rest of the drawing. For features to be drawn to scale on a print, it is necessary that each feature have the same proportion. For example, a line identified as 1 inch on the print will be half as long as a line identified as having a size of 2 inches. Therefore, this 5.5-inch feature is not drawn to scale with other features on the print. Look at this extension line. It has a small box containing a capital letter B attached to it. This identifies this feature as a datum. A datum is a feature that is used as a reference point during measurement. This is called the datum feature symbol. On older prints, you may find this version of the datum feature symbol. It can be attached to an extension line of the datum feature, to the feature itself, or can be noted under the dimensional value of the feature. Datum feature symbols can also be attached to a feature control frame. A feature control frame is a rectangle that contains information that controls the geometry of a feature. You'll learn more about feature control frames in a later lesson. Occasionally, two datums separated by a hyphen may be called out on a part print. This indicates that the two datums are to be combined to form a coaxial or coplanar datum. An example of a coaxial datum would be two diameters of a workpiece that share the same axis. An example of a coplanar datum would be a workpiece where two flat surfaces share the same plane. This is a datum target symbol. In this example, this datum target symbol is used to identify a point which will be used as a datum. They are used when a machined surface or diameter is not available as a datum. One example would be a cast workpiece surface. A datum target letter is shown in the lower half of the circle, along with a number identifying that specific target. In this example, 3 datum targets are needed to define datum X. Therefore, the datum targets will be labeled X1, X2, and X3. Datum targets can be called out as individual points, using an X symbol to mark the target location on the workpiece. When the datum target is an area, the size of the target area is shown in the upper half of the datum target symbol. Datum targets, which are areas, are usually marked with a shaded area on the print. Part 2. Reading and interpreting symbols. Symbols are typically used to identify features and types of measurements on part prints, although abbreviations are sometimes used on older prints. DIA, or D, is used to abbreviate the word diameter. This symbol is used to identify a diameter dimension on modern prints. R is used to abbreviate radius. The radius of these inside corners is called out in this detail view with an R designation. This is a test indicator. It can be placed against a cylindrical feature and read as the workpiece is rotated. TIR is the abbreviation for total indicator reading. TIR is the distance between the minimum and maximum readings of the needle on the dial indicator as the part is rotated 360 degrees. TIR may also appear as FIR for full indicator reading, or as FIM for full indicator movement. TYP is the abbreviation for typical. This means that the dimensional data provided on the print applies to other features on the workpiece which have the same dimensions. Here you can see that this dimension states that this hole should be 1.752 inches from the center line. Because this dimension is labeled with a TYP designation, we know that the distance from the center line to an identical feature should also be 1.752 inches. On modern prints, you will see a number followed immediately by an X instead of the TYP designation. If you see 6X on a feature, This means that this exact feature will appear 6 times at different places on the workpiece. For example, this print indicates these 6 holes each have identical dimensions, but are located in different areas of the workpiece. The letters MAX and MIN may also appear. MAX refers to a maximum dimension, while MIN refers to a minimum dimension. For example, this print calls for a maximum radius of 20 thousandths on this corner. The value may be less than 20 thousandths, but not more than 20 thousandths. The chamfer is the angle of the surface that connects two other surfaces. The abbreviations C, CFR, or CHAM may be used for the word chamfer on older prints. Typically, the size of the feature is noted on the print and is followed by the chamfer dimension given in degrees. For example, the size of this chamfer is 50 hundredths with an angle of 30 degrees. Some prints, however, will note the chamfer angle first and then the size of the feature. You will frequently find pictures or symbols to indicate measurements or features of a workpiece. This marking number on the print notes the quality of surface finish required. Other commonly used symbols include the counterbore symbol, the countersink symbol, and the depth symbol. This print calls for a through hole with a diameter of 100 thousandths. It also calls out for a counterbore on the same axis with a diameter of 188 thousandths and a depth of 110 thousandths. There are many other symbols that can also appear on a print. A reference manual, such as the Machinery's Handbook, can be a useful tool when you encounter unfamiliar symbols. Part 3. The title block and tolerances. A tolerance is the amount of variation permitted on dimensions of a machined part. This is the title block for this print. It is usually located in the lower right corner of the print. The tolerances which apply to most of the dimensions on the print may be indicated in the title block, as well as other information, such as whether the print is intrametric and the scale of the drawing. Be careful. Just because the scale is noted as 1:1 does not mean your print is to that scale. The use of zoom and reduction in today's copiers may mean the prints you receive on the production floor will not match the scale shown. Whether or not your print is to scale, never measure a feature by scaling the print. You will often find this caution written in the title block. On some prints, there may also be a notes area located outside the title block. These notes are numbered and contain special instructions not included in the title block. The ideal size of a feature given on the part print is normally referred to as the nominal dimension or simply the nominal. However, parts do not have to be exactly this size. There is an acceptable range into which the size of a feature must fall, called the tolerance zone, or simply the tolerance. On the part print, the tolerance is typically shown as plus or minus a certain amount from the nominal. This tolerance is plus or minus 60 thousandths of an inch. This means the feature can be 60 thousandths above the nominal or 60 thousandths below the nominal, for a total tolerance of 120 thousandths. With a nominal dimension of 340 thousandths of an inch, the feature can be as large as 400 thousandths or as small as 280 thousandths and still be acceptable. These values are defined as the upper and lower limits of the tolerance zone. On some dimensions, the tolerance is not evenly split. For example, this tolerance is given as plus 1 millimeter 50 hundredths and minus 35 hundredths of a millimeter. The upper limit for this feature is 112 millimeters 63 hundredths, and the lower limit is 110 millimeters 78 hundredths. This type of tolerance is sometimes called unequal bilateral, since the nominal is not in the center of the tolerance zone. Some prints, especially those with unequal bilateral tolerances, will not note a nominal dimension, only the upper and lower limit of a tolerance zone. Notice that on this dual dimension print that the metric equivalents of the upper and lower limits are noted inside the brackets. Occasionally, the tolerance which is allowed is only on one side of the nominal. This is called a unilateral tolerance. There will only be a plus or a minus tolerance amount given, but not both. Some part prints show only nominal dimensions. Typically, on these prints, there will be a note similar to this one which says, "Unless otherwise specified, all dimensions are to be plus or minus 10 thousandths." Some prints, like this one, will have a table in the title block that states the tolerance. Here you see that all values to the thousandth place have a tolerance of plus or minus 5 thousandths. You should always try to produce parts that are machined to the nominal dimension. However, the upper and lower tolerance limits will establish a range of part sizes that will be acceptable, thus preventing you from having to machine all parts to exactly the nominal value. This is a basic dimension. A basic dimension is a theoretically exact and therefore not tolerance dimension. Basic dimensions can be used to show the location of part features, the distance between related part features, or the size of part features. Basic dimensions are typically shown on prints inside a rectangular box. For example, this basic dimension establishes the exact distance between two holes. When a basic dimension is not enclosed in a rectangular box, you will usually find a note in the title block like this one, stating that dimensions without tolerances are basic. This is a reference dimension. Any number on a part print which is enclosed in parentheses is a reference dimension. A reference dimension does not have a tolerance. It is used by a machinist for information purposes only and is not used for machining or inspection operations. Reference dimensions are established from other values shown on the print or are sometimes a repeat of a dimension already given. Reference dimensions should not be used when measuring workpieces. Prints can also be baseline dimensioned or chain dimensioned. Most modern prints will be baseline dimensioned. Each feature on a workpiece will have its own tolerance that will not affect other features or tolerances on the workpiece. For example, each feature is referenced from the left edge on this baseline dimensioned workpiece. The first feature measured from the left edge is 250 thousandths plus or minus 5 thousandths. The second feature is 500 thousandths plus or minus 5 thousandths. And the third feature, the total length of the workpiece, is 750 thousandths plus or minus 5 thousandths. You may encounter some older prints that utilize chain dimensioning. In chain dimensioning, each dimension is measured separately. There is no single feature that many dimensions are measured from. Using our current example, you can see that the distance from the left edge of the workpiece to the end of the first feature is 250 thousandths. The size of the second feature is 250 thousandths, and the size of the third feature is 250 thousandths. Notice that the tolerance for each feature is plus or minus 5 thousandths. Also notice that the total length of the workpiece is not noted on the print. This is called a missing dimension and must be calculated using math. To find the total length, the nominal dimensions of all the features that make up the total length must be added together. Write down the nominal values of each feature and add them together. You can see that the nominal length of the workpiece is 750 thousandths. But what about the tolerance for the total length of the workpiece? When using chain dimensioning, the tolerance of each feature can affect the location of other features on the workpiece. If each feature on this workpiece were at its upper limit of plus 5 thousandths over the nominal, the total length of the feature would end up being 15 thousandths over the nominal value. Conversely, if each feature were at its lower limit of minus 5 thousandths under the nominal, the total length of the workpiece would end up being 15 thousandths under the nominal value. Therefore, chain dimensioning is seldom used because of the buildup of tolerance amounts across multiple features. Part 4. The inch and metric systems. The inch and metric systems with regard to the machine tool industry are both used to measure linear distances from point A to point B. When using the inch system, the base unit of measurement is the inch. The inch is divided into 1,000 equal parts called thousandths of an inch. The thousandth is the key unit of measurement for precision machine parts in the machine tool industry and is written 0.001. You will notice that the inch system can use decimals or fractions to represent measurements smaller than 1 whole inch. Parts that do not require as much precision can be measured in the inch system using fractions of an inch. On modern prints, fractions are converted to decimal numbers. However, you may encounter older prints with fractions. Today, fractions are used only to define cutting tool and thread size. The metric system is based on the meter. If you divide the meter by 10, you will have 10 equal segments called decimeters. Decimeters are typically not used in the machine tool industry, however, but the decimeter can be divided into 10 equal parts called centimeters. 1 centimeter is divided into 10 equal parts called millimeters. You will find that most metric prints note dimensions in millimeters. Centimeters use the abbreviation cm, while millimeters use the abbreviation mm. Notice that 1,000 millimeters is equal to 1 meter, or 100 centimeters. The unit of measure being used is determined by the 1 or 2 letters to the right of the value. Therefore, by simply moving the decimal point, we can state the measurement in any of 3 units: meters, centimeters, or millimeters. Moving the decimal point one place in either direction always represents a change by a factor of 10. Millimeters can be divided into tenths, hundredths, or thousandths. Notice the 0 to the left of the decimal point. This helps to define the value as a metric measurement. Inch measurements typically do not have a leading 0. If you have never measured in the metric system, you need to understand the relationship between inch units of measure and metric units of measure. For example, 1 inch equals 2.54 centimeters or 25.4 millimeters. If you have been making measurements in thousandths of an inch, it is important for you to be able to visualize the actual size of these measurements. A thousandth of an inch is almost too small to see. To understand how small a thousandth of an inch actually is, try measuring some common items. For example, the thickness of a piece of paper from your student guide is approximately 4 thousandths of an inch. Therefore, if you were to divide this page into 4 equally thick sheets of paper, you would have 4 sheets, each one about 1,000th of an inch thick. The ability to estimate sizes of objects is also important. You should be able to look at the part print, visualize the size, and be able to tell if the part is close to the nominal size on the print. You are probably able to make fairly accurate estimates when using the inch system, but it is equally important to be able to make accurate approximations using the metric system. For example, if the nominal size of a feature on the print says it should be 10 millimeters and 55 hundredths, you should be able to look at the feature and determine if it is close to the whole millimeter and that there are no large discrepancies. If the feature looks like it is only 5 millimeters or 20 millimeters, you will be able to visually identify the discrepancy and realize that this is a problem. You may want to relate inch measurements to metric measurements. Remember that 25.4 millimeters is equal to 1 inch. Therefore, 100 thousandths of an inch is equal to 2.54 millimeters, and so on. Look at the features of common objects around you and attempt to estimate their size in millimeters. Then measure with a metric ruler to see how close you were. This completes your training on basic print reading. See your instructor regarding your next step.